also within the realm of the analysis that we do, is we try and evaluate all of the failures that are occurring on a system as best we can. Again, it's one of those things where a lot of times there's many different modes of failures. And what we try, though, and understand is when a system fails, we try and figure out, okay, we normally with the design engineers and the operators will try and figure out why did it fail, what do we need to do different to make sure that it doesn't fail again. From a logistics standpoint, what we do is we try and we see what parts did fail. We do work, as I've said, with the engineers and the operators to try and understand what failed in terms of parts. Was it a failure that was due to a part that for whatever reason reached the end of its reliability, a projected reliability, or did it fail more often than what was necessary? And so what we do is, overall from a logistics standpoint, we're always trying to look at what is what can we do to lower the life cycle costs of that system. So that means everything from development until that system is retired and no longer used. And in terms of doing that, what we do from an analysis perspective then is we try and see, okay, what are the failures that we're witnessing on all of the parts that we spare within the logistics system, and say, okay, well, it's normal. We identify, we try and see, okay, this is the number of failures we're seeing on any of these particular spares, and we try and track a trend to try and see where do we see a growth in logistics costs associated with needing more spares than what we anticipated, or what parts are not necessarily performing the way that we initially, or the engineers initially anticipated. Where is that reliability different than what we initially expected? And so we try and take that and work those inputs from the operations and the logistics operations environment, and then analyze them in our planning and analysis function to try and figure out where do we think there's a potential area for improvement, either us sparing additional quantities of those parts so that we impact operations less, or is there an area where we think we need to take this to the engineering community that's supporting that particular system and say, hey, look, we're seeing a large number of parts for this particular system and this particular part even, and fail, and we're having to procure a whole lot of them. And so is there an avenue here where we could potentially do a redesign of that particular part or of that particular subsystem within the larger system so that we can maybe potentially minimize the costs of the failures that are occurring? As part of the analysis, what we'll do is we'll say, well, this part is failing more often than we anticipated. Again, it's sometimes difficult to understand what is the true reliability of a part if that part doesn't have a large supply chain. So then it would potentially turn into a discussion between NASA and NASA Logistics and the vendors to try and identify, hey, this part that we're procuring from you has an advertised reliability of, let's say, for example, 99%. And yet when we're operating this, it has a reliability of 98%. And while that 1% might seem small, over the course of a lifetime of a system, it could prove to be a large cost depending on what the individual cost of that particular part is. And so if that is a very difficult to procure part because there's not really much of a supply chain for it, then we'll do a lot of discussions with the vendors to try and understand maybe why the reliability isn't what we anticipated. If it's a part that it has a larger supply chain, so it's easier to procure, then in those particular cases we'll say, well, do we need to potentially change the vendor that we're getting this part from? Maybe for whatever reason that vendor isn't providing us a part that's behaving as we expected, and so there's an alternate vendor that we can maybe go to. And usually, though, whenever there's that type of discussion, then we have to go back to the engineering community and say, hey, look, this part that you wanted or that we initially procured to support this system isn't really behaving like we thought it would be. Is this a plausible substitute that we can use, or do we need to do some sort of redesign because the way it's being, the part that was initially bought or procured isn't actually behaving the way we thought it would? What we do here at here at Kennedy Space Center, we have a large variety of parts, but we only procure a small number of each of those parts. So it's really hard to control the life cycle of the particular systems that we use here, because each of the parts, a lot of the parts can be very unique, or there's so few of them that are actually made by the vendors. In the commercial sector, what they do is they try to make a large number of fewer parts. So in other words, what they try to do is when they put a system together, they try and use the same part in as many different places as they can, so that if one part fails, they have a large number of spares available to replace it, and it's also then easier to track the reliability of particular parts. It's easier to change out parts. It's lower cost for each of those parts because there's a large number of them that were made. They can make economic order quantity buys for those parts, so that they could drive down their costs for their particular system, be it a car or whatever it is that they go off and build. Here at Kennedy Space Center, again, because of the uniqueness of the systems that we put together and that we operate, we don't have that same luxury. We don't have the same luxury of being able to say, well, we're going to use this part as here, 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 and here, throughout the systems. We try and drive and strive for commonality, which is essentially what it is. But a lot of times, each of the particular subsystems that make up those systems have unique requirements. Because, again, we're flowing commodities like cryogenic fluids and things that have really high requirements in terms of specifications, that doesn't allow us the flexibility to be able to use the parts as many times as we would like. And so what that does then is it drives up the need for us to go and procure lots of different components, again, not of different types rather than one component many times. So in logistics, we don't do the testing. At Kennedy Space Center, though, we have various systems, from things as large as the mobile launcher, which has its own park site, and so the testing is in part done there. We also have several different test facilities around Kennedy Space Center. We have the launch equipment test facility, which is where we're essentially building and testing all of the umbilicals that go attached to the mobile launcher. And then we also have an electronics development lab, which is where all of the software and the electronic components that go into the electronic racks that then will go into the mobile launcher are all initially tested and fabricated. So there is a level of different level of testing throughout the center, depending on the particular aspect of that particular subsystem that eventually feeds into the larger systems. From an initial design perspective, when a new system is being developed in particular, we have our logistics engineers sit in with the design teams to try and understand what are going to be the requirements to support a particular system. Are you the engineering community developing something that's built with a lot of old parts that are going to be really hard for us to go support, or going to be really costly to go support? Or is it, in some cases, what we do is we generate a list of qualified parts. We call it a qualified parts list. There's other different terms for it. But essentially, it's a list of recommended parts that we think, based on the requirements that we're seeing that system needs to be able to provide, here's a recommended spare parts list that we think we should go off and have on hand and make sure that to make sure that whenever you go off and design and build this system, it can be properly supported. The goal is always really to try and make sure that when we go off and have this system implemented and it's operational, that we've got something that the life cycle costs will be minimized for, that's easily supported, that we don't want a lot of folks standing around waiting on a system that might have broken down and that we can't find a spare for. We want to try and make sure that whatever system is designed can be operated for the least cost possible.